Hey, this is Joe, and this is the second video in the 10th chapter of Stewart's Calculus, and we're going to be talking about polar equations and calculus. So here, again, same kind of deal as in the last video. There are a bunch of equations that are given to you in the book that kind of relate polar equations to calculus, and these are the three that you're going to need to know for the AP. So how to find a tangent, and how to find the area under a polar curve, and how to find the arc length of a polar curve. So, tangent of a polar curve, because a polar equation is basically a special kind of parametric equation, and it's the kind where we have some r is equal to a function of theta, and then we parametrize it by having x equal r cosine theta and y equal r sine theta for any different kind of r. And of course the only thing you need to write out for a polar curve is r equals some function of theta. That's the curve. You can get all this other stuff out of that. And so a tangent, that's dy dx, then based on it being a parametric equation, we have dy d theta over dx d theta, but we can find out a general expression for both dy d theta and dx d theta because the parametrization is basically kind of constant like this. So we can use our product rule. If r, we just substitute in f of theta in for r, we'd use our product rule, we get the derivative of one, leave the other constant, plus the derivative of the other, plus the one constant. So we'll get f prime theta sine theta plus f of theta cosine theta. Cosine's the derivative of sine. And then down here we'd get f prime of theta cosine theta minus f of theta sine theta. And so that's the general expression for a tangent. What I would recommend, however, is just memorize the parametric formula and then kind of apply this each time based on what the r looks like. That's just my recommendation, though. The area formula, this is the formula, and of course for all of these your book gives a nice numerical proof, but this one I'm going to go into deeper explanation on the next slide. But this is broadly how you find the area under a polar curve. And the arc length, I'm not going to really go into much explanation for it. Just know this formula. You can derive it straight from the arc length formula of a Cartesian curve, but this is not terribly difficult to memorize. And then the area is 1/2 the integral of the square of the function of theta times d theta. So now I'm going to kind of explain that area function a little bit better on the next slide. Alright, so let's say we have a circle, and let's say we wanted to find the area of a slice of that circle that looks kind of like a slice of pizza. The equation for that is going to be area is equal to 1/2 r squared theta, and theta is the angle between the two lines that make up the pizza slice. The r is the radius, and then 1/2 of that. So how does this relate to polar equations? Well, this is how we approach taking integrals of polar equations. So let's get this polar curve right here. Sorry, it looks a little ugly. But when we integrate, remember we're integrating with respect to theta, and so theta, different points of theta are all these lines right here. And this is a different value. This is one value of theta, that's theta 1, that's theta 2, etc. So if we want to take the integral between, and this is, we can say that there is theta 3. So let's say we want to take the integral between theta 1 right here and theta 3. The area would look kind of like a slice of pizza, but with a varying radius, with the r being varied. So, as with most integrals, although I'm not going to do the proof here with the limit talk and the summation talk, but basically we can use the same concept, except we make this theta, which this theta, and that theta is really a change of theta, right? Because this theta here, that's a difference. So I'm going to write a change of theta, a delta. So we'd turn that delta into a d theta, because we're going to make them that change approach 0, so make them teeny tiny, then add them up over a bunch of r's, and remember r in polar land, r is a function of theta, so that r, we can make that into a function of theta. We have the same parameter as we're integrating, and then we're going to keep that 1/2, and we're integrating all of this between some a and b. In this case, that a is going to be theta 1, and this b is going to be theta 2. So this is how we're always going to be thinking about area when we're dealing with polar equations, kind of these slices of pie. or slices of pizza or whatever you want, where each of these lines represents a different value, a different r, the length is an r, at a different value of theta, and the value of theta is from this positive x-axis right here, and that's where the theta always comes from. And so that's kind of how you should broadly think of how this area works and how you should rationalize using this area equation. So now, since area is kind of the most difficult part of polar coordinates with calculus, seeing as like the tangent talk and the length talk are basically going to be the same for all parametric equations, and you have to conceive of area with polar a little bit differently. We're going to be doing kind of one of the hardest problems, area problems that you can do with polar equations, and that's going to be a problem where you find the area in between two polar curves. So let's go do that right now. Alright, so we're going to be doing number 26 on page 693 in your book, and this question asks us to find the area between the curves r equals 2 plus sine theta and r equals 3 sine theta, where this equation is going to be on the outside, the first one's going to be on the outside, and then the second one is going to be on the inside. So let's go over and look at a graph of these two equations so we can kind of get an idea of what we're doing. And remember, using graphs with polar equations is always makes them a lot easier. It's a great idea if you're allowed to use it on the test or in the problem set that you have to take home. So let's go check that out. Alright, so here is the graph of these two curves, and we've got the inside circle is r equals 3 sine theta, and the outside curve is r equals 2 plus sine theta. And so what our question is asking us is to find the area between the two curves. So this area right there. And so if you imagine the unit circle outside of here, we can kind of test for points of theta. So that straight up here, that's going to be theta equals pi over 2. Down here, this is going to be theta equals 3 pi over 2. This is going to be theta equals 0, and this is going to be theta equals pi. So what we could do is to find the area under the outside curve, between the outside curve, or under the outside curve, sorry, which would be the entire thing, like everything enclosed by that curve, minus the area enclosed by the circle here. However, integrating around an entire curve like this from point A to the same point can pose some algebraic problems. But since both of these curves are symmetrical, what we can do is just find the area under the curve between of the outside curve between pi equals 2 up here, where they both intersect, and then we're going to prove that they intersect there algebraically, down here to 3 pi over 2, and that's half of the area, and then subtract from that the semicircle under here between pi over 2 and 3 pi over 2. And then find this area, which is going to be half of the enclosed area, and then just multiply that area by 2, and then we'd get the area between the two curves. And so that's what we're going to be doing. So when you see coefficients that are either halves or 2s, I'm going to be very careful to point those out to you and make sure that you're careful about them. So let's go back over to the other screen. We're going to prove that these two curves intersect at theta equals pi over 2, and then from there we're going to start using our new area formula. So let's go. Alright, so in order to figure out that these two curves intersect at theta equals pi over 2, we're going to have to set 2 plus sine theta equal to 3 sine theta. We can subtract over sine theta, and we're going to get 2 is equal to 2 sine theta. 1 is equal to sine theta. When does theta make sine equal 1? When theta is pi over 2. So there you go. Now we're going to use our area formula. And so we're going to say that half of the total enclosed area between the two curves is going to be, and we're using our formula, and we're integrating between pi over 2 and 3 pi over 2, if you remember our graph. And we're going to be doing this first to the outside curve, and the outside curve is 2 plus sine theta, but since that's our function of theta, we have to square that, d theta, and then we're subtracting from that the hemisphere of the circle, and we're also going to need to take a 1/2 out here because that's the formula. and we're integrating also between pi over 2 and 3 pi over 2, but that function is 3 sine theta, so when we square that, we're going to get 9 sine squared theta d theta. So now, before we start integrate, so for now we're only finding half of the area, and we're going to move this 2 over, we're going to multiply it over later. But for now, we need to simplify inside of this integral to start solving, and we're going to do a trig substitution in here, one that we did in the last video, to make this easier to solve. So we're going to get 1/2 integral between pi over 2 and 3 pi over 2, and now let's factor that out. We're going to get a 4 plus a 4 sine theta plus a sine squared theta, and all of that is going to be d theta minus a 1/2, and now between pi over 2 and 3 pi over 2, 9 sine squared d theta. So since the limits on the integrand are the same and we're integrating with respect to the same variable, we can actually, and they're both multiplied by the same coefficient, we can actually put this subtraction sign inside the same integral, and we'll get rid of the sine squared theta. Or not get rid of it, but only have to deal with 1. So we're going to combine this integral, and we're going to get a pi over 2, 3 pi over 2, and we're going to have our 4 plus 4 sine theta, and then a sine squared theta minus 9 sine squared theta is going to be minus 8 sine squared theta, and all of that d theta. So now we can integrate each part of this expression individually. So we're going to keep this 1/2 out here. That 4, when we integrate it, we're going to get a 4 theta. So that's 4 theta between pi over 2 and 3 pi over 2, plus 4, and then we integrate the derivative of what is sine. Well, the derivative of negative cosine is sine. So this is going to be a negative 4 cosine theta between pi over 2 and 3 pi over 2, and then we're going to have a negative 8, and this integral we're going to have to make a trig substitution to figure that out, and that's between pi over 2 and 3 pi over 2 sine squared theta d theta. So let's remember this, and we're going to move on over to the next screen. Alright, so now this is what we've got, and remember this is half the area, but we got a 1/2 here, so why not just get rid of that half, and we'll have the area is going to be equal to this without the half, and we can start evaluating. So 4 times 3 pi over 2, that is going to be 6 pi, and then that's going to be minus a 2 pi, minus 4 times cosine of 3 pi over 2, it's going to be 0. Cosine of pi over 2 is also 0, so that's going to be 0 plus 0. And then this negative 8, I'm going to need to make a little substitution in here, and that's going to be, we did this in the previous video, 1/2 minus 1/2 cosine of 2 theta d theta. So this turns into a 4 pi. Minus 8, and then we're evaluating 1/2 theta when we integrate that. So that's going to be theta over 2 between pi over 2 and 3 pi over 2, and then minus and minus is a plus 8, but then that minus 1/2 we can take out, and that's going to be a minus 4 between pi over 2 and 3 pi over 2 cosine 2 theta d theta. So we're just going to copy this down. And this will become the derivative of sine is cosine, so this is going to be a sine 2 theta, but a 1/2 is going to be out there, and then this is between pi over 2 and 3 pi over 2. And so once we evaluate this all out, which I trust you can do, we're going to get 9 pi over 2. And that is the area between the two curves. So thanks for watching. Stay tuned for the rest of this chapter on polar and parametric equations with calculus, and we're getting mighty close to the end. We've only got one more chapter to go after this, and then that's it for single variable calculus. So get excited. Thanks.